PIC microcontroller, what different things are required to be there? At first, we must know the features of PIC microcontroller. Very limited features were there for 8051 microcontroller, as it was very basic microcontroller, and now we need many more features depending on different applications to be implemented. Okay, and that's why we at first must know what are the features of this PIC microcontroller. After that, comparison and selection of PIC series as per application. Here we are going to learn PIC 18F series. Only one microcontroller we are going through, because obviously the other element in the series, they are having one or two variation in terms of RAM, in terms of ROM, in terms of timer, pulse width modulator, and so on. So what we are going to learn is its 18FXX series. Okay, means 18F series, that keep in mind. So that particular series, its architecture we are going to learn. So what I am telling you is we have to learn the feature. Then whenever you are selecting the microcontroller, it is very important that comparison and selection of PIC series as per application is required. In that PIC series, for example, you have decided for some application you have to go for PIC microcontroller. So you have number of PIC microcontroller. Out of it, which fits for your need, that is required, right? And for that, what is required? You must know its feature. Then only you can think of comparing it. Is it right? Okay. And further, this point which I am trying to tell here is we are going to deal with which architecture? 18F series architecture we are going to deal with. It's MCU, program and data memory organization, pinout diagram, reset operation, oscillator options, what different oscillations are there, what BOD is there, power down mode, and configuration bit setting, timer, and all the things, peripheral support, and everything. That has to be covered for, obviously, for any microcontroller. And here we are going to cover for PIC microcontroller. Okay, now, as we have started that we are studying 8-bit microcontroller. And what do you mean by 8-bit microcontroller? At a time, your microcontroller can process on 8-bit of data. Is it right? That is meant by 8-bit. Okay, if you have longer stream of data, what do you have to do? You have to cut it into part of 8 bits, 8 bits, and so on. And accordingly, you have to process it. Okay, so we are talking about 8-bit microcontrollers. So in that series, what different microcontrollers are there? One is Freescale Semiconductors, which was Motorola. Okay. Then there is one more 68HC08 or HC11. Then Intel 8051 is there, Atmel AVR is there, Zilog Z8 is there, and PIC, which is made by Microchip Technology, PIC is there. So these are majorly used microcontroller in which series? 8-bit series. When you are going to deal with 8-bit series, means your requirement is sufficient, which is fitting sufficiently for what? 8-bit. In that case, these are very good microcontroller. They are there for the comparison. Then, if they are there for the comparison, how to choose any one of them? Depending on requirement. If the requirement is sufficient that it will be implemented by 8051, you can think of going for 8051. If you need something advanced, you can go for the specifications or the features of this microcontroller, and accordingly, you can think for the higher microcontroller in the 8-bit series. So that way, these many names are there. Okay. Now, 1 minute. Criteria for choosing the microcontroller. What we are learning here is criteria for choosing the microcontroller. So obviously, as I'm again and again saying that it is very important, depending on the application, we have to choose the microcontroller. So obviously, some criteria has to be there. So what is that criteria? Meeting the computing need of the task at hand, efficiency and cost effectively. How to meet the need? Efficiently and cost effectively. Both the things are there. In starting only, what I say that if my data is of 8-bit, 8051 or PIC is going to deal with that data, what at a time it can work on that 8-bit data. But if my frame is bigger than 8-bit, then what is required? It has to cut into sections, right? It has to be cut into section and then to be dealt with that data. But now try to understand the frequency with which the data is dealt with by 8051 and by PIC. Again, they are different. PIC is working on higher frequency range. So obviously, though the data is of 8-bit, what is happening with PIC? PIC will do it fast. Are you getting my point? So, criteria for choosing the microcontroller is how efficiently it is handling your computing need. And that is the example I gave you now. Is it right? Now, obviously, we are looking for efficiency, but along with efficiency, cost effectiveness is very important. Okay. Obviously, in our project, we have to buy just one microcontroller to work on that one microcontroller. It's okay. We are spending more money on that microcontroller. We are asking for more features and spending more money. But when the product has to be made, in that case, when the product has to be made, number of microcontrollers are required to be there. So in that case, we must care for cost effectiveness. Is it right? That's why efficiency as well as cost effectiveness are two important things. Okay, then availability of software and hardware development tools. Now, in many cases, the thing is happening as we are saying for VLSI also many times it is happening that those front end and back end development tools they are not freely available. Okay, and that's why it is hard to access them to learn the things. So some other way has to be adopted, make doing some courses, going to some particular classes where you can handle those software and hardware which are costly. Okay, so that's why what is happening in case of microcontroller, we also need to check for the software and hardware development tools. Okay, and what are those? Those are compiler, assembler, debugger, and emulator. Okay, so we need to 1 minute. 1 minute. I'll come back. 1 minute. Okay, so it is already shared. It is visible to you. Again, put it on full screen mode. That is better. Okay. So is it okay? It is visible. Sorry for disturbance. So what I'm saying is we have to think of what development tools are available and what type of development tools: compiler, assembler, debugger, and emulator. Okay. By the name itself, you will be getting what these different tools are there. Just I will tell you know these three tools. If not, try to find it at your level. Can anyone tell me what is emulator? What do you mean by emulating the circuit? So for today's lecture, these four tools, these names, obviously I know you people are knowing it, but then also I'm keeping it for you people. Please try to find out what do you mean by these tools? What do you mean by compiler? Many times we take this name. I have the compiler, I have the assembler, debugger, might be emulator you have not dealt with, but emulator also. So please, this is the question for you. Try to find out the answer for it. Then wide availability and reliable source, obviously. So that is one thing we have to consider for. Then, other than that, what is my heading criteria for choosing the microcontroller? Now, meeting the computing need of the task at hand, efficiency and cost effectively, which was the first point which we have taken in last slide. How we are going to find out computing need? Determine its type. Is it 8-bit, 16-bit, or 32-bit? Right? So my requirement, what is my requirement and how is my microcontroller? Is it 8-bit, 16-bit, 32-bit? That we have to find out. Then the speed. Speed means the frequency at which your microcontroller is working. Then packaging, how it is packaged. Is it DIP? Is it QFP? What type of package it is? Because again, I am making my circuit, and for the circuit, what I am thinking of, what type of package I need. Okay. So depending on my requirement, obviously, I'll be choosing the pin. So how was 8051? It was DIP package, right? Dual inline package. And what do you mean by QFP? It is quad flat package. Is it right? Quad. By the name itself, you'll understand it is quad, and on all the sides, pins will be there. That way the packaging is. So what type of packaging we need? Then what is our requirement of power consumption, the amount of RAM and ROM, number of IO pins and timer, cost per unit, ease of upgrade. All these things are determining the criteria. Is it right? Criteria we can think on our own. What is my criteria? For what application I am using it? And depending on that, I have to find out what are the criteria. And then I have to move to what? Microcontroller. Will my microcontroller fitting in these criteria? Then we are going to choose that microcontroller. Is it right? Then again, the same slide with more points I am putting here. This was there in 8051 also. What is it? RISC and CISC comparison. What are the characteristics versus, or just try to understand that what are the characteristics of RISC and CISC microcontrollers. Okay, and you very well know what is RISC. It is a reduced instruction set controller, and this is what complex instruction set. Now look here. When I say reduced instruction set, how are the instruction? Simple instruction, and they are getting executed in one cycle, right? In reduced instruction, whereas complex instruction taking multiple cycle. That is the main difference. Okay. Then in RISC, only load and store access memory. By what two instruction we are accessing the memory? When we are loading from the memory and when we are storing in the memory. At that time only we are accessing the memory using these two instructions. Whereas in this complex instruction, any instruction may access memory. That is the difference. And that's why complexity is coming to the instruction. Are you understanding? Then design around pipeline. Okay, reduced instruction, how they are designed? They are designed around the pipeline. What do you understand by this? Means how the data is flowing around it is designed. Whereas this is designed around instruction set. Okay, that is the difference. Again, instruction executed by hardware. And here, instruction interpreted by microprogram. So, complexity is coming out to be here. Whereas here, what is happening? The hardware. What hardware is there? Maybe accumulator is there. Maybe ALU is there. Maybe the register bank is there. Using it, your instruction is getting executed. Whereas in this case, what is happening? At first, that complex instruction will be interpreted by microprogram, and that microprogram will send the simplified instructions to your ALU, to your register, and will tell what to do. That is important difference, right? Then fixed format instructions. Instruction will be having the fixed format. Registers to be put at first, accumulator later on, and so on. Whatever is the format, that is fixed. Whereas this one has variable format instructions. Here, few instructions and modes. We are saying it is reduced instructions. So obviously, mode of operations are also less, as well as instructions are less. And as this one is complex, it will be having many instruction and many modes of operation. Okay, direct mode, indirect mode, that way. Different modes of operation can happen. And in this case, in RISC case, you will be having few instruction and few mode. So at the assembly level, it is easy for a human being to understand it. Is it right? Then complexity in the compiler for doing all these things. Look, we want the working by RISC similar to that of CISC. Okay, so Till this point, it is simple. So who is handling the complexity? Complexity in the compiler. Compiler is handling the complexity because we want our program to be simple. Simply the person can write down the program. But you want the complex thing to be implemented there. So who will work for that complexity? The compiler will work for the complexity. And in this case, in case of CISC, complexity in the micro program is happening. Okay, the micro program, which is decoding your instruction, there it is handling the complexity. In case of RISC, you have multiple register set. We have seen in 8051, right? 4 register sets were there. Whereas in CISC, there is single register set. This RISC, it operates 50 to 150 megahertz, whereas the CISC operates from 33 to 50 megahertz. So obviously, a lower range of lower frequency range is there in CISC, whereas RISC is acting at higher frequency range. Is it right? That is again the difference. So again, either to choose the RISC or CISC will depend on what application, what frequency you need for your application. For some fast application, obviously, you will be going for the RISC type of microcontroller. And while talking about this RISC and CISC, again, we have to just once recall the von Neumann architecture and the Howard architecture. So, while talking about this architecture, just I'll recall what we mean by von Neumann architecture. We have program and data memory in common. Is it right? Program and data memory is in common. Okay. So the address, for example, I have to access the program memory. Through the address, I'll be sending the address of program memory, and through this bus, I'll be accessing that program, which will be executed by ALU instruction by instruction. If I have to access the data, again address I am sending by same bus, and on this bus, I'll be accessing the data. Are you getting? That way, the program and data memory is common. So bandwidth is limited. Is it right? Same bandwidth we are using for data as well as for the program. Okay. So do you remember this type of structure? We dealt with this structure in our 8051. There also we learned what is von Neumann architecture. So von Neumann architecture fetches instruction and data from single memory space. Thus, we have limited operating bandwidth. Okay. And recall that remaining thing. What different remaining things are there connected with the microcontroller? There are IOs. Okay. There are I and O. Right? And internally, what is there? Control logic is there, ALU is there. In total, you can call it to be central processing unit. And what do you have? Memory. How is this memory? Combined memory for program and data. Some part for program, some part for data. Okay. So that is von Neumann architecture. And the next architecture, standard architecture, is Howard architecture. In this Howard architecture, check this diagram. You have data memory, you have program memory. For program memory, address bus is separate, data bus is separate. For data memory, again address bus is separate and data bus is separate. So limitation on bandwidth will not be there. Okay. So faster working you can expect from this type of microcontroller. So uses to separate memory spaces for program and instruction data. Improved operating bandwidth allow for different bus width. Is it right? I can think of this bus width of 8-bit. This I can think of 16-bit, right? So different bus width is possible there. That is only the difference. So what we learned how to select the microcontroller. What next we learned? We learned what are the RISC and CISC processor. We have seen the difference between RISC and CISC processor. After that, in short, we have seen what is von Neumann architecture and what is Howard architecture. Okay, coming to our PIC microcontroller. And as I say, many features are there for the PIC microcontroller. We have to understand these features. Okay, because look, features are making the internal structure of your microcontroller. That is architecture of microcontroller. So when we have to understand the architecture, that architecture is supporting all the features, right? So we must at first know what are the general features. What are general features? What are peripheral features? What different protocol it handles? All these things we have to understand. We have to read the name at least for them so that we can think of internal structure. Right? Now look. Generally, how is the microcontroller? It is CPU, that is Central Processing Unit, having ALU and control unit, that is CPU. Then this CPU is communicating with memory, right? This memory can be data memory, program memory, that way it is communicating. What other thing is happening? This CPU is communicating with I/O ports or the bus, internal bus. That internal bus is communicating with what I/O port. What do you understand by I/O ports? Input or output port. These pins, how I want it. I want it as input or output that can be decided by programming these ports. So CPU through the internal bus, it is communicating with I/O port. Other than that, what your microcontroller generally have, it has timer. So they are showing three timers, means PIC has three timers. So they are showing three timers. Okay, timer, oblique counter, we have seen. Later on, we'll check it, how many timer, how many counter, and so on. Now, one more important thing is coming out to be there, which is PWM, pulse width modulation. So two units of pulse width modulations have been shown here in the diagram. Why we need this pulse width modulation? Whenever we have to think about speed control, we have to think of pulse width modulation. So my microcontroller, whenever it is driving some mechanical part where I have to deal with speed control, I need pulse width modulation. By changing the width of that pulse, you can control the speed of that, maybe motor, whatever it is, you are controlling its speed. Okay. Other than that, you have A to D converter, analog to digital converter. In some cases, the input which are coming to me, they are directly, they are not digital. They are directly not digital. They are analog. Okay. From some sensors, I am getting my requirement. I don't have to search for such some ADC externally to be connected. Internally, the ADC is there. 10-bit ADC is there, which is going to convert your analog signal into how much resolution? 10-bit of the signal with that much resolution. Okay. So your analog signal will be converted to digital with how much resolution? 10-bit of resolution, and will be passed to your CPU for further working. So that is A to D conversion. Do you got the importance of it? Why we need it? Because in many cases it will happen that my sensor is giving me, or I am sensing something, I am taking input of something which is directly analog. Then what to do in this case? What is the other way if your microcontroller is not having A to D converter internally inside? Externally, you have to put the chip of A to D converter, and it is taking more time, more space. Is it right? Taking more space on your system. Your system become comparatively bulky. So what this microcontroller is doing internally, it is giving A to D converter to you. Other than that, you have USART. We have seen USART, that is Universal Synchronous Asynchronous Receiver Transmitter in 8051. This for serial communication, for long distance communication. Same thing is available here. So with PIC is dealing with this protocol also. Okay, so just from this diagram, I tried to tell you what different things are there in the microcontroller. One more important thing I would like to tell here, that few new names are coming in front of you. Okay, few protocols are coming, and protocols are important thing to understand, because protocols are the standard way set up by the industry so that we can deal with type of protocol, maybe CAN protocol. For long distance communication, USART like protocol has been used. So what is happening? Industry have set their protocol, and when we are implementing our embedded system, depending on application of our embedded system, in which domain it fits, Does it fit in automotive domain? Does it fit in serial communication domain? Does it fit in some other domain? Depending on that, it is expected that we are dealing with those protocols, not going just for input and output of the data. We are dealing by the protocol. That is important. That will be of value in industry. Okay, so after this diagram, I'll come here to the general features. Okay, and what features are there? Pick 16C or 17C. This series are 8-bit microcontroller by Microchip. And what type of technologies they are using? CMOS, right? Complementary MOS technology they are using. MOS is the advanced technology which has been used for manufacturing the microcontrollers. Even I would like to say that the MOS technology, after transistor TTL technology or ECL, the MOS is nowadays developing technology. Okay, I'll not talk about the MOS. So MOS is complementary metal oxide semiconductor technology which has been used. Then PIC are popular due to high performance, low cost, and small size. All these three things are there. High performance. Okay, that is important thing coming here. It uses high speed RISC architecture. So clearly, what architecture? RISC architecture. And that was the reason in last slide we have seen what are importance of RISC architecture. Okay, it has 33 single word instructions. At the assembly language, how many instructions are there? 33 single word instructions are there. Operating frequency for this particular series. Actually, now what is going to happen as we go on changing the series, operating frequency will change. So obviously depends what microcontroller you want, what you are choosing. You have to find out what is its frequency range. So 16C DC to 20 megahertz is the frequency range. Okay, can add external program memory up to 64K words. Okay, how much? 64K words. This much external program memory can be added to the internal memory, whatever is available. Okay, then some advanced version include ADC with 4 to 8 channel, as I have shown here. What is it? This is the advanced one, and it is having 4 to 8 or 10-bit of ADC. General feature include timers. We know what are timers. Watchdog timers. Okay, it is watching the program. It will watch the execution of the program. So name is watchdog timer, embedded ADC. These are general features. Extended instruction oblique data memory. What can happen? More instruction as well as data memory is available. Serial communication is available. Pulse width modulation, ROM, EEPROM, EEPROM memory. All these are extendable. You can extend it. So that is how your PIC microcontroller is there, which can be used for a very, what you can say, high performing application, or the application which need high performance. There you can think of using it. Okay, so look, in this case we talked about 16C 16C series, 17C series, and now on this page I'm talking about PIC 18F series. Okay, how it is high performance. Last one also was high performance, but it has enhanced flash microcontroller. Flash memory is there with what type of protocol? CAN protocol. Again, this question I'm keeping for you people. Find out what is CAN protocol and for what type of application CAN protocol is used. Okay, now coming to the feature of this 18F, this is the main we are going to discuss max. So it is what? RISC processor, 8-bit data bus, limiting to what? 8-bit. 16-bit instructions. Okay, same was the thing in case of our 8051, 8-bit data bus, 16-bit instruction. But look, how much ROM? 2 megabyte of ROM is there. And as it is 2 megabyte, how many address lines will be required? 21 address lines will be required. Okay, then 4 kilobyte of data RAM. Okay, and as we are saying 4 kilobyte of data RAM, how many lines are required to address them? 12 lines to required to address them. Are you understanding this thing? Do you got it? What happened? Then, as we are saying, 32K flash ROM is there. Flash memory, how much? 32K. This is faster memory. Okay, flash means what? It is the fast memory. You can access it fast. You can work fast with this memory. How much? 32K flash ROM is there. Okay, other than that, 1536 byte SRAM is there. That is static RAM. It can be used as scratch pad. Okay, you can write on it, you can rub it. Okay, so that way, like a scratch pad, you can use it. What we say in 8051? Those register bank, they were used as scratch pad. Right? We can write it, then we can erase it. Similar way. 256 byte EEPROM or storing critical information. So these many things are there. Just for 1 minute, I am keeping this slide in front of you. Obviously, it is not possible to keep in mind what different things are there. But we must know RAM, ROM. We have to interlink 2 megabyte, why 21 address lines are required. 4 kilobyte, why 12 address lines are required. So give thought for 1 minute to it, think about it, and we'll go further. Okay, right? So is it possible for you to relate 2 megabyte? Hmm? It is the stack of how many bit on one another? 8 bit. But till what you have to go? For 2 megabyte, you have to go. And for addressing those 2 megabyte, we need 21 address lines. Okay, in diagram, it will be much clear. I'll go for further thing, few more features. You'll be tired of features. Those many features are there in case of microcontroller. And these are general features of the architecture. Look, 10-bit, 8-channel ADC. 10-bit ADC means it is giving resolution of how much? 10-bit. Your one point will be resolved in 10-bit. Okay. And how many channel, how many different AC signal you can check for? Sorry, not AC, analog signal you can check for. 8 analog signal you can check for, right? So 10-bit, 8-channel ADC is there. So you can deal with 8 different input. You can give them to your ADC, and one by one, by sampling way, it will convert them to digital and will be available as the input. USART is there, as well as in this 18F, you have 4 timers oblique counter. All the timer, all 4 timers can act as counter. It seems to be like this. So how many? 4 timers are there. How many were there? In 8051, 2 were there. And now by 2, it is increasing. 4 timers. How many IO ports? 5 ports are there. Out of it, first one is A port. And it is of how many pins? It is of 6 pins, 6 IOs. Okay. B, C, D, they are of 8. And E is of 3. So check 8 3s are 24 plus 6 plus 3. In total, you have 33 IO lines. Dealing with interfacing with the external world, 33 IO lines are available. And in total, how many ports? 5 ports are there. Okay. Then DC to 40 megahertz clock input. It operates on this range of frequency starting from DC up to 40 megahertz. If you remember, for 8051, approximately 12 megahertz was the clock. So obviously, this is working at higher frequency. Do you remember what is meant by this? Higher frequency means machine cycle will be faster and the further operation will be faster. Is it right? Has 16 bank register with 256 entries. Okay, so in one bank, in total, how many? 16 bank register with 256 entries. Okay, so again, more registers are available for saving the data temporarily. Is it right? In 8051, only 4 were there. Here, 16 bank of registers are available there. Then there are GPR, means general purpose registers, and special function registers. You can change the value of them, and you can change its location, variable. Variable means you can put the GPR here and there in the register bank, whereas SFR, they have the fixed location. Is it right? Special function register and general purpose registers are available there. Further, as we say, this 18F is high performing microcontroller. And when we say it is high performing microcontroller, how it is high performing microcontroller, that we are going to check here. So high performance RISC CPU. It is linear program memory addressing up to 2 megabyte. More is the program memory. Obviously, more the program memory, bigger program you can save there and deal with that bigger program. Linear data memory addressing to 4 kilobyte. 2 megabyte is the program memory. And how much data it can address? 4 kilobyte of data it is addressing. So both way performance becomes more. Up to 10 million instruction per second operation. Right? Up to what? 10 million instruction per second. This is one unit of calculating the speed of operation. So this much is the speed of operation. In 8051, we are not calculating generally by MIPS. Here, it is the high performance. And thus, for computing its performance, we are saying that 10 MIPS operation is happening here. Then, we have seen this. DC to 40 megahertz is the clock input. Further, 4 megahertz to 10 megahertz oscillator clock phase lock loop is one of the important features required in the microcontroller. Whenever it is coming further, we will go in detail of it. So what is it? PLL, phase lock loop. And for that phase lock loop, for what range of frequency it is active? For 4 to 10 megahertz range. Then 16-bit wide instructions and 8-bit wide data path. Okay, your instruction is of 16-bit and data path is of 8-bit. Priority level for interrupts. You can set the priority of interrupt, which interrupt is required at first and later on. Then 8 by 8 single cycle hardware multiplier. This is extra thing which is available there. What can happen? 8 by 8 single cycle hardware multiplier. In 8051, multiplier was not there. Hardware multiplier was not there. So if you have to do the multiplication operation, how it is happening? Your ALU is doing shifting and adding. Try to understand how is the multiplication? Shifting and adding will give multiplication. So who is doing it? Your ALU is doing it. And in every cycle, shifting will there. In the second cycle, adding will be there. If you have 4 bits, so 4 times shifting, 4 times adding will be required. So those many iteration will be required by your ALU to do that operation. Whereas if you have hardware multiplication in a single cycle, 8 by 8 bit will get multiplied and you will get the output. So that is beauty of hardware multiplier. So in PIC 18F series, you have 8 by 8 hardware multiplier. Directly it is available. You can give the 8-bit, other 8-bit, its multiplication will happen and you will get the output. Whereas what is going to happen if this hardware multiplication is not there? It will happen by adding and shifting, adding by and shifting, and those many cycles, that much time will get wasted. And that is how we are saying that 18F is the high performance microcontroller. Okay, then. Now, the other features which we are going to check, they are related to peripherals. Okay, the peripherals, the thing which we can connect to our microcontroller. So, depending on their requirement, how the peripherals requirement can be satisfied by this microcontroller that we are going to check. So look here. The first one is high current sink oblique source. Means when as the input, when you are configuring your microcontroller as the input, your pin becomes in pin. I pin you are making instead of I and O. What you are making, your pin becomes in. So you are sinking the current in that case, right? So how much current you can sink from that circuit? 25 milliampere current you can sink. For example, I am connecting some switch, and to that switch some voltage is connected. So when I am turning on that switch, what will happen? My pin, microcontroller pin is acting as input pin. I programmed it as input pin. So how much current it can sink is 25 milliampere, and it is very good value, very large value. Okay, same thing. As I am configuring my pin as the output pin, and on the output side, if I am connecting some LED, and if that LED needs, or how much current can be sourced by that LED? 25 milliampere current can be sourced by that LED. Are you getting the point? 25 milliampere sink as well as source, high current sink as well as source is possible in case of 18F. Now, compared to this, at your level, try to find out what is happening with 8051, and you will understand why we are saying high current sink and source is happening here. Then, 3 external interrupt pin. How many external interrupts? 3 external interrupt pins are available. Okay. How many we can set? 3 externally interrupts we can set in case of 18F. 4 timer modules are there from timer 0 to timer 3. 0, 1, 2, 3. That way, 4 timer modules are available. And we'll check how are these timer. Timer 0 module, how it is? It is 8-bit timer. 8-bit oblique 16-bit timer oblique counter. It can work as timer. It can work as counter. It can be configured as 8-bit. It can be configured as 16-bit depending on our requirement with 8-bit programmable prescaler. We can prescale it. Is it right? Already we can divide it by some value. We can prescale it. Is it right? So that can happen with timer 0. What about timer 1? It is 16-bit timer counter. Only 16-bit. Here is a chance of 8-bit. In the second case, there is no chance of 8-bit. Only 16-bit we have to deal with. But it can be a timer or can be a counter. You very well know that timer is for setting the delay. For what counter is there? For measuring the external event, counter is there. Is it right? Timer is using internal clock frequency. What counter is doing? Clock is the external event which is coming to the counter. That is acting as a clock for counter. That is the difference, right? Timer 2 module. This is 8-bit timer oblique counter with 8-bit period register. Okay, look here. It is having some different function. It is timer counter, but for 8-bit. And remaining 8-bit with 8-bit period register. This is time base for pulse width modulation. I told you that important feature is there in case of it. Now, this PIC microcontroller, it is pulse width modulation. And for that pulse width modulation, this 8-bit of timer 2 is used for setting the base, time base for the pulse width modulation. Timer 3 module, it is 16-bit timer counter, right? So in this way, we have 0 to 3 timers, okay? 0, 1, 2, 3. And look to the beauty, how beautifully the distribution is there, how beautifully the pulse width modulation has been introduced in it. So this is how the timer and counters are there. Then secondary oscillator clock option. What is the secondary oscillation clock option? One clock option is the crystal oscillator which has been connected to the PIC microcontroller. Other one is timer 1 or timer 3. Even they can act like the clock to your microcontroller. That option is also available. You can set the clock frequency. Set the clock frequency by setting the bits in that timer, we know how to set the delay in the timer. Delay means what? One particular frequency we are delaying by some value means we are getting a new frequency. So that frequency can act as the oscillator for the microcontroller. In the peripheral feature, as we have to control the peripheral, we have capture, compare, and PWM module, which is generally called as CCP module. Okay, what is it? Capture. For capturing the external event, comparing at the level of timer, we can go for comparing pulse width modulation for controlling the speed for that. So this is very important feature. CCP module is available there. So whenever we are going for timer, we are going in detail with it. CCP is important feature for automotive type of the application. CCP pins can be configured as capture input. Okay, it is of 16-bit max resolution, 6.25 nanosecond. Max resolution of how much? 6.25 nanosecond. And capture input, 16-bit capture input is there. Compare 16-bit max resolution, 100 nanosecond. PWM, what it is doing? Resolution is 1 to 10 bit. And maximum PWM frequency, if you are going for 8 bit of resolution, it is 156 kilohertz. And if you are going for 10 bit of resolution, it is 39 kilohertz. This we have to go in detail whenever we are going for the timer. But these are very important peripheral features which the PIC 18F is dealing with. What features? CCP. Important is capture, compare, PWM. And these are the detailing of either capture, compare. I told you, capture means what? Capturing the external event. So with what resolution it can capture? That has been told here. Compare. At the level of timer, we can think of comparing. And PWM is for speed control. Okay, keep that thing in mind. Again, with this peripheral features dealing with peripheral, enhanced CCP module, which has all the features of standard CCP module, but also has following feature for advanced motor control. Okay, what is available? Enhanced CCP. In that enhanced CCP, you have 1, 2, or 4 PWM output, pulse width modulation output. Selectable PWM polarity. So all these are dealing with what? PWM. I'll keep it like this only. In timer, we will deal with it. Then, other than that, this one more name I want to put in front of you, Master Synchronous Serial Port, MSSP, with two modes. What two modes are there for this serial port? One is SPI, 3-wire SPI. This is again one protocol which support 3 wires SPI, or it also support 4-wire SPI. This is one protocol supported under serial port. And what is other protocol? I2C protocol is again supported under this serial port. Last thing is addressable USART module. Try to understand how many different names are coming in front of you. So you people have to go for these names: PWM, CCP, MSSP, then SPI, I2C. They are coming here and there in the application. So if you know these names, you will understand how important they are. And that is the reason I'm putting these features in front of you. Else it is possible for me directly to go to what? The block diagram of the microcontroller. But we must know this name. If we know the name, we can think of the application. Okay. So after PWM, what is there? MSSP, that is Master Synchronous Serial Port. And under this serial port, we have SPI communication or SPI protocol, which can be handled by 18F, as well as I2C, which is master and slave type of protocol that is handled here. Okay. So look, CAN, SPI, I2C, all these are the protocol. USART, USART, these protocols are handled by what? By the 18F microcontroller. Look how many added features are there. How much importance we are adding here to the 18F. Okay, then the other feature are analog. Okay, after those peripheral feature. In short, we talked about the analog, but here bit detail will go for the analog. 10 to 8 channel ADC converter or ADC is there with conversion available during sleep time. When the microcontroller is sleeping, during its sleep time, this conversion is happening. Means we are not utilizing the uh, what we can say, we're not adding any delay to our program during the sleep mode. This ADC is working. How is this ADC? It is of 10-bit and up to 8 channel of analog signal it can handle. Okay, 8 channel available. This is the important thing. And what particular I am saying, it is fast. It is fast. Why? Because it is utilizing during the sleep time. Analog comparator module. There is one more module called as analog comparator module, which is available. Programmable input and output multiplexing can happen in this analog comparator module. Then comparator voltage reference module is there. Programmable low voltage detection is available. This supports interrupt on low voltage detection, right? And programmable brown out reset is available. These are all the analog things which are available. Look here, just we'll take this programmable low voltage detection module. What this module is doing? It will generate the interrupt if voltage is going below particular value. Supports interrupt on low voltage detection. If the low voltage is detected on some pin, maybe on the whatever we are watching on that, if the low voltage is generated, then interrupt is generated. That is called as programmable. We can program it, low voltage detection. We can set the voltage and that low voltage can happen to be there. Programmable brown out reset. If some if the brownout is happening, you can think of resetting. So again, you can program it and can think of resetting your circuit, which is called as brown out reset. Okay, so these are all the analog things which are dealt with in this 18F microcontroller. Then we were talking about one protocol, CAN protocol, right? CAN bus. Have you heard this name, CAN bus? CAN bus protocol or CAN, have you heard it? In what application it is there? Do you know? Do you know CAN trans receiver module generally where it has been used? So automobile electronics is basically using this CAN protocol. Okay. So compile with ISO CAN conformance test message bit rate up to 1 Mbps. Okay, anyway, it is giving in detail about the CAN. And obviously, as CAN is not known at this level to you, it's okay. Just keep in mind that what it can deal with in detail, it can deal with CAN bus. Okay, and all these things are there while dealing with the CAN bus. Then, features of the microcontroller related with flash memory is also there. So look, power on reset is there. Once you're turning on the power, reset will happen. Power up timer is there. And oscillator startup timer is there. You can ask, once the power is on, you can ask your timer to start with, that is available. Oscillator also to start with can be asked for. So these things are available there. Then there is watchdog timer, keeping the watch on some timing with its own on-chip RC oscillator. Programmable code protection is there. Power saving sleep mode is there. Selectable oscillator option. What different oscillators are there? 4 PLL of primary oscillator is possible and secondary oscillator of 32 kilohertz clock input. So these things are available there. Phase lock loop gives you very accurate frequency. For some application, we need very accurate frequency. We don't want the changes in the frequency. So the phase lock loop will provide it. And that's why the phase lock loop is generally used, which is available here in 18F. Okay. Similarly, in-circuit serial programming is possible. What type of in-circuit serial programming? When the microcontroller is in circuit, at that time you can think of programming it via two pins. Such two pins are given. You can get it programmed. No need to take out that chip, put it on the programming board, get it programmed. No need. You can program it when it is in circuit. Low power, high speed, enhanced flash technology, flash memory is there, and it is low power as well as high speed. Fully static design, wide operating voltage range. It is operating from 2 volt to 5.5 volt. Industrial and extended temperature ranges are available. And look how much is there in this microcontroller. It becomes so after one advanced microcontroller we are learning here, and you will get it that how many applications can happen on this microcontroller. You can use it anywhere in any type of application for different protocol. You can deal with it and can use it. That's why it is required that we must know the features. Now here is the slide I'm putting in front of you, showing some series of 18F with variable RAM, ROM, EEPROM, IO pin, ADC, timer, and how is the pin package. Okay, so this is just the comparison which can help us to select the microcontroller depending on our requirement. Is it right? So this is the slide. I'll not read it, obviously. No need to read it. Many things we know. So just check. This is the comparison of PIC 18 family. So what you are finding as the um, microcontroller is becoming advanced and advanced like this. PIC 18F1220, then 2420. It is the advanced series and advanced and advanced. What is increasing? Flash memory is increasing, which is generally the programming memory, ROM memory for code, and which is the faster memory. Is it right? RAM is increasing. Obviously, data memory is increasing. EEPROM, that is erasable, means more program we want to store, and that's why this PROM is also increasing. More IO pins are coming out to be there. ADC is almost remaining constant. Timers are increasing in some case. In last case, timer increases. And what is changing is the how is the pin packaging. That is also changing. Actually, size reduces in this TQFP, whereas in DIP, because you have just pin on two sides, and that's why it is a big pin, big chip comparatively. And TQFP, you are having the pin on all four sides, and that's why the size is also reducing comparatively, right? So this is how the comparison is there for PIC 18 family. Coming to the architecture of PIC microcontroller. Do we continue or to stop? Okay. So for half an hour, I'll continue and then. Okay. So architecture, PIC 18F microcontroller architecture we are talking about. So as we have seen, PIC microcontroller are designed using Harvard architecture, which include MPU, means microprocessor unit, program memory for instruction, data memory for data, IO ports, support devices such as timer, support for serial communication. Okay. So in total, these things are required to be there in the diagram when we are checking for the architecture. Right? So by this way, now before going to diagram, have to clear here. We know one accumulator was one register, working register, which work in conjunction with near to the ALU in case of 8051. What was its name? Accumulator was its name. And in case of PIC microcontroller, there is 8-bit W register. It is called as working register or WREG. By this name, it has been used. It's most widely used register in fifth microcontroller. Okay, you can call it as accumulator. It is same. So whatever data we have to operate on, whatever data is going to the microcontroller for operation, we have to bring it to this W register. Similarly, it is having the same operation, that of the accumulator. It is used for all arithmetic as well as logical operation. To understand use of WREG, we are going for some instructions or some examples which are trying to tell it. Look here now. So there is one instruction, move LW, and the instruction we are writing. What we are doing? We are moving the literal to W and then writing the, look, it is like this, move LW, what? 8-bit of data. This is the instruction. In total, how is my instruction? Move LW, and here I'll be writing the 8-bit data which I have to transfer. That data may be from 00 to FF. Anything can be there in hexadecimal. Again, here we have to deal with hexadecimal. Okay, look here. Move LW 25H. So in hexadecimal, how much? 25 is the data we are going to move. It moves 8-bit data into W register. What this instruction is doing? It is the instruction in assembly language, which can be understood just by that hardware. Which hardware? And what it is understanding by decoding it? Move LW 8-bit of data. It moves 8-bit of data into W register. 8-bit data value, I told you, it ranges from 00 to FF. L stands for what? Literal, which means instruction is dealing with actual value. Whatever will be given here, it is what? Actual value. Look, some instructions are there where the memory is addressed. But here, when we are saying L means what? We are addressing the actual data which is here. We are not addressing any memory to take the value from that memory. We are not saying like this. We are saying that whatever is data given here, consider it as the data and move it to W. That is what L is trying to say. It is similar to immediate value used. Okay. This is what we are saying, immediate value, move that immediate value to the W register. So in total, how will bit move LW 25H? Means 25H value will be moved to W register. This W register is of how many bit? 8-bit. So what will be there in those 8-bit? 2 means what? 0, 0, 1, 0. And further, 5 means what? 0, 1, 0, 1. So 8-bit of this W register will be 0, 0, 1, 0, 0, 1, 0, 1. That way the values will be available there after executing this instruction. Right? Now, look, again in assembly language, one more instruction I am showing you here, and it is what? Add LW. What this instruction is saying? It is saying that add the literal which is given in the instruction with the value available in W. Adding, asking to add the literal given by 8-bit data to the value available in W. Add 8-bit literal value into W register and store result where? Again in W register. So that is how the instruction is there. To perform addition, for example, the instruction is, look, we'll go for this two instruction. Move LW 25H. What we are moving in this W? Value 25H. Add LW 34H. Means what? To the 25 which is there in W, 34 will be added. So 25 in hexadecimal plus 34 in hexadecimal will give 59 in hexadecimal. So finally, after this addition operation, what will be there in W? There will be 59. How will be the 8 bits which are there? 5 means what? 0, 1, 0, 1. And remaining 4 bits, 9 means what? 9 means it will be 1, 0, 0, 1. Is it right? 5 means 0, 1, 0, 1. And 9 means 1, 0, 0, 1. Is it right? That is how the W will be filled. So these two operations will be executing in this way. Okay. Then there is one thing called as file register. The PIC microcontroller has many other registers. They are called as data memory space. In PIC literature, the data memory is also called as file register. Just to understand, it has been there. So what is it? Many registers are there. And it is the data memory space and it is called as file register. By what name we are going to call it? By the name file register we are going to call it. And after getting those things here, I am coming to the architecture of PIC microcontroller. Okay, PIC 18F, and which one in that 18F? 452. Its architecture is there in front of us. Okay, so we'll go for this architecture. We'll try to understand this architecture. Many names we have taken in the features, and that's why we can understand this architecture. So look here. There is ALU. What is here? Arithmetic Logic Unit. It is next supported by what? W register. Is it right? This is the 8-bit W register. Output of ALU is storing in this W register. Okay, as well as W register is connected as one of the input register to ALU. So 8-bit from these W registers are directly available to ALU. And what about the other part which is coming for the operation to the ALU? It is coming from this MUX. This MUX can select from what? From this bus which is available there, or it can be from the instruction. Whatever is the data from the instruction will come here. Are you getting? Externally we can take it. And externally from where we can take it? We can take it externally from IOs, from counter, from peripherals, or internally from the memory part of the instruction, which is data will come out to be here. Are you getting? So that is how this is most important part of your 18F microcontroller, because here is the execution happening. Whatever you want to do, here is the execution happening. Is it right? So that way the execution will happen. Now, remaining are all supporting things. Is it right? Look, flash program memory. What I told you, program memory which is fast, that is flash program memory. Here program will be there, one by one instruction will be fetched. Okay, program counter will tell which instruction to go. Stack is there along with that program counter. So one by one the instruction will go, instruction will get decoded. Data part of the instruction will be available to the MUX so that this will operate, right? Instruction decoding will happen depending on that, either burnout, reset, watchdog, startup timer, low voltage protection, debugger. If they are included there in the program, they will act. They will be supported by what? Timing generation, which is the clock. It will be supported. Okay. So this is how the program part is dealing. Other than that, we have RAM. This is for data memory. Okay. This RAM is again supporting what? It is updated by your program counter. Okay. This RAM, externally data can come. You can save on it. From here, you can give it to the external IOs, right? From the RAM, it is possible. Even look here, instruction register. The instruction register can ask for, give the address, and can ask for some data from the RAM, which will be going to. I may miss something, but that way, either dealing with the internal data, either dealing with the external data, dealing with the programs, everything is happening here, and it has been tried to show here in the diagram, right? Now, what different things are there? In the peripheral, you have counters and timers. They have the connection, both way connections with your bus, which is internally flowing there. You have IO ports. These IO ports, they have external IOs. You can configure them as input, you can configure them as output. Similarly, many peripherals are also there. right? Again, those peripherals have the input or you can give them the output. So that way, this is the architecture of 18F, which is comparatively bit complicated than 8051, which was a simple, straightforward processor. And why the thing is happening? As we are adding more functionality, the complexity is adding. Obviously, the thing is happening. Now there is one status register. Can anyone tell me what do you understand by the status register? Do you remember we talked about the status register there in the 8051 also? So this is the status register, which will show the status of the program. That is the status register. Okay. Any name missing? Stack we have seen, RAM and file register we have seen, and everywhere try to understand that mux are there, which have the chance of selecting either from the output or from the input. What to deal with that selection is there. Here also mux is there, which is in conjunction with what? ALU. The chance of selecting between the data coming from our memory or along with the instruction or coming from the output. That selection is available here in the architecture. Okay. So this is the architecture of PIC18. Now, we have seen at the level of diagram, we'll check some theory points. So instruction register, part of CPU control unit which holds the instruction currently being executed. That is instruction register. Now, what is happening? I have to go back. Look, this instruction register I am talking about. I told you one by one instructions are coming here. So what it is holding? It is holding the instruction which will be part of CPU control unit which holds the instruction currently being executed. Only one instruction. In instruction cycle, the instruction is loaded from where? From the program memory into instruction register, right? One by one it will be coming. Then what the instruction decoder is doing? Again, after that instruction register, there is instruction decoder. It decodes the instruction in instruction register. Decoding include determining where its operands are in memory, retrieving operands from memory, allocating resources to execute the command. Everything is required, right? Decoding means you are getting the instruction. For example, the instruction was move LW. What was it? Move LW 25H. We are asking literal value 25 to be moved to W. Okay, direct value we were transferring there. So it is required to determine what is your operand, where is that operand present, retrieving operand. If it is the memory, you have to retrieve it from memory and allocating the resources for doing all this. This is done by whom? By the instruction decoder. Okay. This is further detailed diagram telling in same diagram, same you can say the architecture, but with the detailing. With the detailing means how many bit of data bus is there, what about the direct address, what about the program, how many lines of program memory is there. That way, everything is given in detail in this diagram. So shortly, I'll talk about this diagram and then we'll stop here. So your W register, I'll come here, which is heart of the microcontroller, W register. It is of how many bit? 8 bit. So that 8-bit data through this bus is going to your ALU. On the other side, again, from the outside, how many? 8-bit you can take, or the data which is coming from here, again, it can be of 8-bit. So your ALU, what we are trying to tell here is your ALU is dealing with 8-bit of data, 8 and 8-bit in total for all logical operations as well as all arithmetic operations. That way it is dealing. Now your ALU, it is updating the status register. What is the status of the program? Is there any carry generated? Is there any flag generated? Okay. All those status have been updated here. How many? 3-bit of status. By 3-bit, it is updating your status register. By checking the status register, part of the program will decide either some interrupt has to be generated, some timer has to be started, some timer has to be stopped, or what. That will depend on the status register. Is it right? Then, okay, so this part is done. Then come on this side. What is it? Flash. How is your flash? 512 by 12. This can be the flash memory, or 1024 by 12. That much is the flash memory. Means it is stack of how many bit? 12 bit. And how many? In first case, 512 times those 12 bits are available, or 1024. Higher memory or lesser memory. That is only the difference. So this is the flash memory available here. Either this or this, depending on which series we are talking about. So how many bit at a time we are getting here? 12 bit. So our instruction is of 12 bit. Where it is going? Single instruction to the instruction register. Okay. One by one, that instruction is going. Who will tell which instruction to go? This program counter will tell. Address bus for program memory. And this program counter will tell. Okay. So that instruction register instruction is going. It will be decoded in instruction decoder and control. It will decode it and it will tell the other devices how to act, as well as it will tell what part is going to your ALU for working. So it is getting decoded, allocating the resources as well as the literal whatever are there to the ALU for working is happening by this instruction decoding and control. Okay. Then look what are here. Device reset timer, power on reset, watchdog timer. All these are available here, which are connected with external VDD and VSS, because their work is like that, either resetting or keeping the watch. Okay. As well as for resetting MCLR bar. That is clearing bar. By giving 0, it will clear the device. So that way it is available there. Then to this watchdog timer, what other inputs are available? You need the clock. So clock oscillator 1, clock oscillator 2, or internal clock. They are available here. Okay, internal RC oscillators. They are available here, and they are further going to this device where the clock is required, the working is required. Further, now what is remaining? This RAM is remaining. How is your RAM? 25 by 8 or 41 by 8? Because it is of 8-bit. RAM is, data is of 8-bit. So that is RAM. Obviously, it is extendable, but this much RAM has been shown here. And what we are putting here? The data, either reading the data from here or writing, fetching the data from here. We are doing like that. So data bus, which is dealing with external IO, it can save depending on the instruction in the program, right? It can give it here, or something can be fetched here or given as the output to GPIO. Is it right? That is how data is acting like, depending on the requirement in your program. What is remaining? Anything remaining? Timer. This is timer 0, and we know that different timer, 4 timers are there internally inside, and we can set the delay with help of those timers. This is how your detailed block diagram is there for PIC microcontroller. There is one, this is remaining. From instruction word address, direct address of 5-bit can be extracted, and that by that also we can access the RAM. That is also one important thing which is happening to be there. These 5-bit and remaining indirect addressing, and this is direct addressing and indirect. Actually, in instruction, 2 ways are there. One is direct addressing, other one is indirect addressing, and that has been shown by these things. Okay, directly instruction direct addressing, it is accessing the RAM, or by indirect addressing, you can think of accessing the RAM. 2 ways are there. What do we mean by indirect addressing? Means we are telling the memory location from where we have to fetch the data. And in direct addressing, directly we are telling that this data has to be fetched. That is the difference. Either telling the memory location or directly telling what to fetch. Okay, so I think for today we'll stop here, and next time we'll go with further detailing of this PIC 18 microcontroller. Okay, with the memories and other detail, we'll go further. May I stop here? Many slides. It is many slides are this. Uh, 1 minute. I'll come out of it. 20-25 slides are there. Next class, we will complete with the other. Yes.